Okay, so continuing our work on Newton's laws and connected particles. There's friction in this question. There's some awkward angles in here. It's going to be resolving of vectors. So this is taken from 2016 ordinary level paper. Lots of stuff in here. We're going to be drawing force diagrams. We're going to be looking at force equations, solving those simultaneously to find accelerations and tensions, and then using our master equations to find the last part. So it says masses of 8 and 12 are connected by a taut, light, inextensible string. Okay, so it's inextensible, tension constant throughout the string. It's not elastic, nothing's bouncing around. It's light, its mass is negligible, we don't have to worry about it having any mass. It's taut, which means it's at full extension here. There's going to be no snap when it suddenly becomes taut. That's already happened. The 8 kilo mass lies on a rough horizontal table, rough meaning there is friction. The coefficient of friction between the 8 kilogram mass and the plane is 3/4. That's 3/4. The 12 kilogram mass lies on a smooth plane. That's smooth, no friction there on that inclined plane, which is inclined at an angle of alpha to the horizontal, where tan of alpha is 4/3. The system is released from rest, shown in separate diagrams. The force is acting on each mass. One thing that jumps out at me always every time I see tan alpha, tan of alpha is 4/3, so opposite to adjacent in the ratio 4/3. If you know your your Pythagorean triples, I should say, you should see that that third side would have to be 5 in there, or you could use the theorem of Pythagoras. So if that's alpha, straight away I can say that sine of alpha is 4/5 and cosine of alpha is 3/5. And really, even without drawing it out, every time I see tan of alpha is 4/3, I know opposite 4, adjacent 3, hypotenuse has to be 5, sine 4/5, cosine 3/5. And you want to get to that stage where you're able to kind of do a lot of that stuff in your head. Showing separate diagrams the forces acting on each mass, we would be doing that anyway to find the acceleration and the tension. So we're going to draw our force diagrams. We're always going to give them a bit of a label, force diagrams. And they're pretty straightforward. Hopefully at this stage you're used to these things. So we've got a force diagram for our 8 kilogram particle and our force diagram for a 12 kilogram particle, and that's what we're looking at here. Force diagram for the 8 kilogram particle, and we're going to have a look at that. Well, the most obvious force always acting on any object is the force on the object by gravity, which is actually known as the weight of the object, which is always mass times little g. Now I'm just going to take, because it's an ordinary level question, they always take little g to be equal to 10, so I'm going to take g to be 10 here. So 8 times little g, 8 times 10, that'll be 80 newtons of force acting downwards. Acting upwards, there's a force on the object by the plane. Contact force there, always perpendicular to the plane, and that's going to be whatever the normal reaction is. We'll come back to that in a moment. Also, there's a tension, there's a force on the object by that string, and that's called a tension force. So the force on the object by the string is called the tension force. And then this kind of intended motion for this 8 kilogram is to go left. It can't possibly go right. So any friction that's going to be taking place is going to be acting to the right. And we have a maximum possible value for friction, which we'll work out. Notice those 4 forces. The up forces have to equal to the down forces because it's moving along a horizontal plane. So the up force or must equal to 80. Or must equal to 80. It has to be. If it wasn't, then the particle would be either accelerating upwards or downwards, which it's not. The other thing is, the question is about acceleration. So there's obviously some acceleration, which means that friction has achieved its maximum possible value. And the maximum possible value for friction is always mu times r, where mu is the coefficient of friction, r is the normal reaction. So it says the coefficient of friction between the 8 kilo mass and the plane is 3/4. That's 3/4. multiplied by the normal reaction, which you can see is 80. 3/4 of 80 is 16 newtons. So there's a friction force here of 16 newtons. And that's my force diagram for my 8 kilogram mass. Fairly straightforward. You got to know a few little things in there. So the 12 kilogram particle may be a little bit more complicated given that it's sitting on an inclined plane, but we go through each force one at a time. The force on the object by gravity is called its weight, and it's always equal to the mass of the object, 12 times little g, which in this case we're taking to be 10. That's an approximation, so I'm just taking that as 120, 12 tens, 12 g's. There's always going to be a force on the object by the plane, a contact force, always acting perpendicular to the plane. That's called the normal reaction. We'll have to resolve the 120 in order to find what that is. There's a force on the object by the string here, that's called the tension force, and that's the same T, that's the same tension force as is acting on the 8 kilogram. That tension is constant throughout the string. It's an inextensible string. So this is what we're looking at here. In order to think about the normal reaction, I'm going to resolve this weight force down here into its perpendicular and parallel components. Okay, so one thing to remember is, and again I'm hoping at this stage that you see that's alpha. We used a little bit of geometry to work out that had to be alpha. This is alpha 90. This is the same shaped triangle as this. This is similar triangles. The ratios of the sides here will be 3:4:5, where 3 is the adjacent angle, 4 is the opposite, 5 is the hypotenuse. So if I know, similar triangles, I can figure this out. Okay, 5/24 is 120, so 3/24s, which will be 72, will be the adjacent, and 4/24s, which will be 96, I think. 4/20 is 80, or 4 is 16, yeah, 96 will be the opposite. If I don't know that, I can just always remember that the adjacent is equal to hypotenuse times cosine, the opposite is equal to the hypotenuse times sine. So the adjacent here will be the hypotenuse 120 times cosine 3/5, which gives me 72, and the opposite will be the hypotenuse 120 times sine of the angle 4/5, which will give me 96. Okay, so those are my force diagrams there. That's everything I need to know. Now my next thing is to come up with my force equations based on those force diagrams, work out acceleration, work out tension, and then use my master equations to figure out the speed. Okay, acceleration will be constant here because the tension is constant. So that's what we're looking at. So we're looking at our force equations based on Newton's second law, which says F net is equal to ma. So I'm going to generate two equations from these two pieces of information. Okay, notice there's no friction in this second one. The inclined plane was smooth, so I don't have to worry about friction. Okay, I do know that the or here is equal to 72. It has to be equal to the force down into the plane. It's not going to really tell me anything. If there was friction, that would be very important detail. So I'm going to look at my two equations. First one from my 8 kilogram mass. We already have the up forces equal to down forces, so I'm just going to look at the forces left and right. And again, just looking back at the picture here, the 8 kilogram mass is going to be moving to the left. So I'm going to call this a left positive system. And this one, if I look at this force down here, this second object, this is going to be moving, trying to move down parallel to the plane. So I'm going to call that the positive direction for this one, and that's how I'm going to develop my force equations. So parallel to the plane here, positive force T, negative force 60. So my net force T minus 60 is equal to the mass. Well, the mass we said was 8 kilograms times little a. That's the acceleration due to gravity. Second one over here, notice the positive direction. I'm going to say 96 is the positive force parallel to the plane. T is the negative force. I'm going to get 96, subtract T. And that's equal to the mass of the object, 12, times the acceleration. So we've generated a couple of fairly straightforward, little system of equations. I'm going to solve that. And how do I solve it? Well, I start by adding, using the addition property of equations, which says if equal quantities are added to both sides of the equation, then the two sides remain equal. Adding here will cancel the t's to leave me with 96 subtract 60, which is 36. 8 added to 12a, well that's 20a. And solving there for a is going to be 36 over 20. Okay, so 4 is a factor of the top and the bottom. That's going to reduce to 9/5 meters per second squared. Of course, it's all approximate based on the fact that I've approximated g to be 10. It wouldn't be exactly quite that. So a is equal to 9/5 meters per second squared. That's what we're looking at. That's the acceleration of the whole system. And that was part 1. Part 2, it was actually part 2. Part 1 was to draw the force diagrams. Part 3 was to find the tension and then find the common speed after 2 seconds. So the next thing we're going to find the tension. Really important to note is that this is constant. 9/5 is a constant. It's not dependent on anything else. It's just fixed. Because it's a constant, that means I can use my master equations of kinematics when calculating speeds and distances and times and that kind of stuff. To find the tension, well, this is part 3. To find the tension, of course, probably should have labeled this part 2. The tension, well, from equation 1 here we can see the tension, make T the subject of this formula. It's going to be 8a plus 60. I'm just going to substitute in my value for a here, which is 9/5. Okay, so 8 times 9/5, well, that's 72/5 plus 60. Okay, expressing that as a single fraction, that's going to be 372 over 5. My units there will be newtons because that is force. That's a unit of force. So that's the tension in the string, 372 over 5 newtons. Of course, if you prefer to decimalize these things, your 9/5 is 1 4/5, which would be 1.8 meters per second squared. So if you prefer to do that, that's absolutely fine. And then 372/5 would be, I think, 74.4 newtons. So if you prefer the decimal version, that's absolutely fine. The last part of the question said to find the acceleration of the system after 2 seconds. You just scroll up and double check that I'm writing that. Find the common speed of the masses after 2 seconds. Sorry, find the velocity of the whole system. So find the velocity of the system when t is equal to 2. Well, we know that the acceleration is 1.8. We know the initial velocity is equal to 0. It's released from rest. We know the acceleration is constant. Since the acceleration is constant, that means that v is going to equal u plus at, where v is the final velocity. Of course, u is 0, so it's just going to be a times t. It's 1.8 multiplied by 2, which is 3.6 meters per second. Okay, so lots really in there, but hopefully nothing overly challenging. Again, take it one step at a time, draw your force diagrams, complete your force equations, solve those equations simultaneously, find your values for A and T if necessary. I didn't actually need T to find the final part, but I was asked for it in the question, and practice. So lots of practice, and we should be finishing that section now after this class, really.